Hello everyone. We are starting with the topic that is electrophilic substitution in benzene. Now, first of all, the question comes like, say, for example, if we talk about the alkenes have a pi bond, and that is why they undergo electrophilic addition reaction. Why is it so? Because the pi bond is a weak bond, that is why it can easily be broken, and this pi pair of electron will be acting as the source of electron for the incoming electrophile. So that is how it undergoes electrophilic addition reaction. So in case of benzene, because there are three double bonds, so we expected the same to happen in benzene also. These three double bonds are there are three pair of pi electrons, so all these should be the weak bonds, and that is how it should undergo electrophilic addition reaction very readily. But no, it doesn't undergo electrophilic addition reaction, it undergoes electrophilic substitution reaction. So why is it so? Why does it undergo electrophilic substitution reaction, not addition? Because the pi pair of electron or the pi electrons are not free, or they are involved in resonance, they are involved in delocalization. So because pi electrons are involved in delocalization, not free, that is why they don't undergo electrophilic addition reaction. No electrophilic addition in benzene, just the substitution. Now we are starting with the examples of electrophilic substitution reaction. Examples, we are starting with electrophilic substitution in benzene. Electrophilic substitution reaction, we have various examples of it. Like, we can talk about the halogenation first of all. Now what about the halogenation reaction, how the reaction is? First, we are doing first example, halogenation. Halogenation means substitution with halogen. So how will it take place? We will take the benzene on reaction with one of the halogen, like say maybe we are doing chlorination, so plus Cl2. The reaction will take place in presence of a Lewis acid. The Lewis acid used may be anhydrous AlCl3, or it may be if, say for example, if we are doing bromination, then it may be FeCl3, or it is, sorry, FeBr3, or it may be AlBr3, etc. So that is how the catalyst can be taken, and we will be getting the compound that is chlorobenzene. So one of the hydrogen from here is being substituted by Cl and plus HCl. So this is one example of electrophilic substitution reaction. Now moving to the next example of electrophilic substitution, it may undergo the sulfonation reaction. Now what about the sulfonation? Sulfonation means we will substitute the hydrogen of benzene by the sulfonic group, and sulfonation is always carried out in presence of concentrated H2SO4, or you can say fuming sulfuric acid. What is this fuming sulfuric acid? That is exactly anhydrous, or you can say H2SO4 in presence of sulfur trioxide fumes, or you may say it is oleum H2S2O7. So in presence of that, the sulfonation reaction will be carried out, and the product obtained here will be benzene sulfonic acid. Benzene sulfonic acid, we may see that hydrogen of the benzene is being substituted by the sulfonic group. So benzene sulfonic acid will be the product obtained, plus H and OH from here will combine together to give water. So this is another example of sulfonation, electrophilic substitution reaction in benzene. We may have nitration also. Now what about nitration? Nitration means the substitution of hydrogen from benzene ring will be done by the nitro group. So we may have benzene, and nitration is always done with the concentrated nitric acid, the mixture of the two, that is nitrating mixture it is called as. What is this nitrating mixture? Concentrated HNO3 in presence of concentrated H2SO4. So that together they are called as nitrating mixture, and they will be giving nitrobenzene. NO2 plus H2O. Or we may carry out Friedel-Crafts reaction also. Friedel-Crafts. Now this Friedel-Crafts reaction is of two types. It may be Friedel-Crafts alkylation or it may be Friedel-Crafts acylation. Friedel-Crafts alkylation. What does it mean? That hydrogen is being substituted by the alkyl group. So how the reaction, whenever we have a Friedel-Crafts reaction, reaction will always take place in presence of anhydrous AlCl3. So we should be very sure that if we are carrying out the Friedel-Crafts reaction, the catalyst will always be anhydrous AlCl3. So how the reaction is going to be Friedel-Crafts alkylation? The reaction will be, we will take benzene ring, and say if we want to bring the methyl group here, we will take methyl chloride. Say if we want to bring the ethyl group here, we may take ethyl chloride. So accordingly, whatever the alkyl group we want to bring on the benzene ring, accordingly the alkyl halide can be chosen here, and the reaction will take place in presence of anhydrous AlCl3. And the compound obtained here will be, hydrogen will be substituted by the methyl group and we will get HCl. So toluene will be the product. Now if we carry out Friedel-Crafts acylation, now what does it mean, Friedel-Crafts acylation? The H will be substituted by the acyl group or by the acetyl group, that is CH3CO group. So how the reaction will be carried out? It will be benzene plus CH3COCl, and because it's Friedel-Crafts reaction, so the catalyst must be anhydrous AlCl3. Hydrogen of the benzene will be substituted by COCH3 group, and that's how the compound obtained here will be acetophenone plus HCl. So that is how the examples of electrophilic substitution reactions. Now what about the mechanism of this reaction? How the reaction will take place? So whenever we do the mechanism of the electrophilic substitution, let me tell you, there are 3 steps common. Now what are these steps? For the mechanism of electrophilic substitution, there are steps common. What are these steps? Number 1, that is generation of electrophile. Generation of electrophile. Second step is formation of carbocation. Now third step is, that is deprotonation. So that is how there are always 3 steps in the electrophilic substitution reaction. Now let's start the examples. We are taking the together all these reactions. Say for example, I am taking halogenation, Friedel-Crafts alkylation, because all these are almost similar types. So that is why I am taking all these together. Friedel-Crafts alkylation and Friedel-Crafts acylation together. We'll do all this side by side. Friedel-Crafts acylation. Now first of all, we should know the reaction. What are these reactions? This is benzene plus Cl2 in presence of anhydrous AlCl3. The compound obtained is chlorobenzene plus HCl. While here benzene plus CH3Cl in presence of anhydrous AlCl3, the compound obtained is methyl benzene, or you can say toluene plus HCl. And here in this case benzene plus CH3COCl in presence of anhydrous AlCl3, it will be acetophenone. So these are the reactions. Now let's do the first step. What is the first step? That is generation of electrophile. Now how electrophile is generated in all the 3 ones? Here anhydrous AlCl3. What is the nature of anhydrous AlCl3? This AlCl3 is electron deficient compound. So in case of halogenation, Cl is the reagent and AlCl3 is the electron deficient compound. So that is why it will cause the heterolytic cleavage of this bond. That is why this pair of electron will be moving towards this chlorine, and this chlorine along with its pair of electron, will go to AlCl3, and that is how what we will get. We will get AlCl4 minus plus Cl plus. So this Cl plus is what? This is the electrophile generated. Chloronium ion is the electrophile generated here. Now moving to the next. Say for example, we are doing it in the Friedel-Crafts alkylation. What will be in the Friedel-Crafts alkylation? In the Friedel-Crafts alkylation, the step can be written in this way. That is, here we are taking CH3Cl. AlCl3 will cause the heterolytic cleavage of this bond. Chlorine, being more electronegative, will be carrying this pair of electron with it, and that's how it will be converted to AlCl4 minus plus methyl carbocation. So this is the electrophile generated. Methyl carbocation is the electrophile here. Now what about in the Friedel-Crafts acylation? How the first step here? Here we have the reagent, that is CH3COCl. Now CH3COCl we may write like this also, so that we may better understand, like this, plus AlCl3. Now it will cause the heterolytic cleavage of this bond. The Cl will go along with the pair of electron, and that's how we are left with CH3C double bond O, this carbon carrying a positive charge, plus AlCl4 minus. So what is the electrophile here? Electrophile is this acyl carbocation. This is the electrophile here. So that is how the electrophiles are generated in all the three. AlCl3 is acting as the electron carrier here. It takes away the electron along with the chlorine. Now we are moving to the second step. Now what about the second step? That is formation of carbocation. How the carbocation formation take place? Now this electrophile will be attacking on the pi electron present in the benzene ring. Now let's say the benzene ring is like this. Here is hydrogen present. With all the 6 carbon, hydrogen is present, but I am writing that hydrogen specifically where the carbocation will be attacking. Now in case of halogenation, the carbocation is Cl plus ion. So this pi pair of electron will be shared with it. Now what will be the carbocation formed here? The carbocation formed will be like this. These two pi bonds will be as it is. This pi pair of electron is shared with chlorine, and that's how there is a positive charge present on it. Now this positively charged carbon will withdraw this pair of electron towards itself. That is how the next resonating structure formed here will be like this. This will remain as it is. This pi bond will remain as it is, and this pi bond is shifted here. And that's how this carbon will become positively charged now. Now this positively charged carbon will withdraw this pi pair of electron towards itself. That's how the next structure, next carbocation structure, the resonating structure formed will be. Here is HCl, no change. Here there is no change in this pi bond, and this pi bond is shifted here, and in turn this carbon become positively charged. So what are the these are the canonical structure of this carbocation, and the resonance hybrid we may write in this way, HCl, and the positive charge is revolving from this carbon to this carbon. So this is the carbocation formation. Same way the carbocation is formed in the other case. There you may show that what is the way it will be. Say for example, I am writing for halogenation. So how is it going to be? Say this is the benzene ring. Or let's write the double bond in some other way so that we may better learn. Say methyl carbocation. This is the electrophile. So this will be attacking, and this will be sharing, say, this pair of electron. Now what will be the carbocation formed here? This pi bond is not disturbed. This pi bond is also not disturbed. Only this is being shared, say H here, CH3 here. And the other carbon who was sharing the pi bond or pi pair of electron will become positively charged. So this is the one carbocation formed. Now this positively charged carbon will withdraw this pi pair of electron towards itself. So that is why the next resonating structure formed will be like this. This won't be disturbed. HCH3 will remain as it is. This double bond will also not be disturbed, and this double bond shifted here. That is how this carbon now become positively charged. Now this positively charged carbon will withdraw this pi pair of electron towards itself. So that is how the next resonating structure of carbocation formed will be like this. This is not disturbed. It should remain as it is. Now this pi pair is shifted here. Now this pi pair will remain as it is. So here the carbon will become positively charged. And what will be the resonance hybrid? Resonance hybrid will be something like this. H here, CH3 here, and the pi pair of, the positive charge is revolving from here to here. So in this way we may have, in case of this alkylation, Friedel-Crafts alkylation reaction. Now if we talk about the acylation, in case of acylation, how the generation of electrophile, or you can say the second step is that it will be like this. This is the benzene ring. It will share the pi pair with this carbocation. This will be shared like this, positively charged. Now the carbocation formed will be having these resonating structures. These two pi bonds will not be disturbed. This will become HCOCH3, and this carbon is positively charged. Now the next structure will be, this positively charged carbon will withdraw the pair of electron towards itself, and the next structure is going to be, this won't be disturbed, will be as it is. This pair shifted here, this will remain as it is, and the positive charge will be here. Now the next case, this will be shifted here, and that's how the next structure is going to be like this. HCOCH3. This pi bond shifted here, this will remain as it is, and here is the positive charge. And the resonance hybrid will be something like this. It is HCOCH3, and the positive charge is revolving from this carbon to this carbon. So this is all about the formation of carbocation. Now what about the third step? The third step is deprotonation. So how this deprotonation will take place in case of the three? Like in case of halogenation, how the deprotonation will be there? It will be, this is the carbocation we have, that is HCl. Here are the double bonds, and here is the positive charge. So this is the carbocation. Now in presence of AlCl4 minus, which was formed in the first step. Now what will happen? This hydrogen ion, this hydrogen will be removed in form of hydrogen ion. So the pair of electron will be shifted here, and that's how is it going to be? This will become chlorobenzene. These two bonds are as it is, and this became a pi bond, and here it became AlCl3. AlCl3 is generated back, and plus HCl. So that's how the reaction gets completed, that is halogenation. Now how is it taking place in case of Friedel-Crafts alkylation? In case of Friedel-Crafts alkylation, the carbocation was like this. Say it is HCH3, and here are the pi bonds. So this is the positively charged carbocation. Now again AlCl4 minus will come, and it will take away the proton. It will move out in form of proton, and it will be giving its pair of electron to this carbon. So that's how here it will become a double bond. So how is it going to be? Methyl is present as it is. This double bond, this double bond, and this double bond. So it is toluene, plus this H will combine with AlCl4 minus to form AlCl3. AlCl3 will be generated back plus HCl. So that is how the deprotonation will take place in presence of Friedel-Crafts alkylation. Now what about Friedel-Crafts alkylation? How the reaction is taking place in case of Friedel-Crafts alkylation? Acylation, sorry. Here, how the step is this? This is like, say, HCOCH3. Here are the double bonds. Now AlCl4 minus will come again and will take away the proton. So this will be moving in form of proton and this pair of electron will be shifted here. That's how the structure will become in this way. Double bond, double bond, double bond, and it is what? Sorry, it is COCH3 acetophenone plus HCl plus AlCl3. So that's all about the mechanism of the electrophilic substitution, that is halogenation, Friedel-Crafts alkylation and acylation in benzene ring. Thank you.